All right, howdy everybody. In this video, we're going to go over a couple of relatively straightforward mechanisms, actually one mechanism, the one shown here, to convert the fully protonated form of phenolphthalein into the doubly anionic form of phenolphthalein. And for those of you that have run titrations in the lab, you probably used phenolphthalein as a pH indicator, and you may distinctly remember it changing its form from the fully neutral colorless form to the anionic kind of bright fuchsia or purple form. When you add that last couple of drops of sodium hydroxide, you get the very clear color change. And so one thing that's awesome about organic chemistry is we can actually start to explain that with some structures. And as those of you who've done titrations know, sodium hydroxide is all you need to make this reaction go. Now, there's actually one of two possible mechanisms that are arrow pushing mechanisms that you could draw for this transformation. Generally, this kind of content might be the most familiar to students who are starting on aromatic substitution chemistry and who are really good at resonance. So I'm going to start with that mechanism. The second mechanism might make more sense to you at the end of the semester after you've talked about acyl substitution and ester hydrolysis reactions. Okay, and so of course with sodium hydroxide, we know that this is the basic form. And so what we're going to do here is just put OH minus as our base. And so we can simply deprotonate one of these nice phenols. This is a nice time to remind us about our pKa's. And so the water in equilibrium with hydroxide plus H plus should have a pKa in the 15 range. And phenolic oxygens, remember, are more acidic than your average alcohol. So a phenol with the phenoxide plus H plus should have a pKa, roughly around 10 maybe, but certainly much more acidic than water is, and so hydroxide should have plenty ability to deprotonate that phenol. So that's one really important thing, is to remind you that phenols are not regular old alcohols. They tend to be much more acidic. Okay, so then we can deprotonate that, and this is just going to take me a little bit of drawing here to get the phenol deprotonated like this. And then often with charges, we like to go downhill if we can. And so one fun thing to do with that is to use resonance. And we can actually use that O minus to push off the ester containing oxygen way on the other side. And so we can use these electrons and then kick off that O minus group. So that would get us to something like this. For those of you that recognize it, the part I'm going to highlight here in yellow should look kind of like a quinone intermediate. Sorry, I used the green highlighter instead, apparently. But that looks sort of like the functional group of a quinone. If we wanted to give this a more specific name, we would call it a paraquinone methide intermediate. Because the bridging double bond is para, and the methide means that it's a carbon-containing quinone instead of the more common oxygen-containing quinone. And so just so you know what I'm talking about, this is benzoquinone up here. All right, and so that would be a reasonable motif, and that gets us a good chunk of the way to our product. And what's fun about this is that we're actually going downhill in pKa. So acetic acid, if we want to add that up here to our pKa list, being deprotonated to H plus and acetate ion, this has a pKa roughly about 4.75. And so again, we're going from a more basic group in the form of hydroxide to a less basic group in the form of phenoxide, all the way down to the least basic group that we have here in the form of an acetate or carboxylate anion. So that's kind of nice. All right, and then to complete our mechanism, we need a second equivalent of NaOH. So we can use that to deprotonate the phenol and go to the doubly deprotonated product. The really fun thing about this, though, is recognizing the resonance structures and being able to connect all of the arrows in this first step that I'll highlight over here. And so this, to me, is one of the more fun elements, is just to get all those arrows all together in one step. And for whatever reason, that's particularly gratifying to me, and to be able to recognize very long-range resonance effects. And if that's not obvious to you, just feel okay about going through and drawing them all one at a time. So maybe I can do that right now and just do that piecewise for us. Push that down, move one electron pair up. And since these are resonance structures, I'm going to use my resonance arrow. Now I can do another resonance structure. And now that that negative charge is right next door to the leaving group, I can use it to push the leaving group off. And so that's a little bit more about how we could complete that mechanism, if you'd like. All right, so there's a second mechanism that I kind of mentioned a little minute ago. And so I'm just going to redraw the phenolphthalein molecule. In its fully neutral form. So here we go. In this case, then we can have hydroxide. And for those of you that have already undergone or seen the idea of ester hydrolysis or an acyl substitution mechanism, you can recognize that we have this carbonyl here. And so this carbonyl is an electrophile that can be hydrolyzed with base, and here we have base in the form of hydroxide. And so we could think about initiating this mechanism by having hydroxide attack that lactone or ester carbonyl. Oops. And so we would make a tetrahedral intermediate that's part of an addition elimination mechanism that's common to the acyl substitution. And so then we could just imagine having this attack down and collapse off to make our product. And so now we could imagine that this reaction goes basically through the exact same steps before, where we have a proton transfer. And now we could imagine having hydroxide as the base, and I'm just going to slide up the page here a little bit. Balance that out with some water. And now I can push off that OH minus as a leaving group, which isn't usually the best leaving group, but for those of you that have gone through the acyl substitution mechanism, you've probably also been through the aldol condensation. And in the aldol condensation, we do end up losing hydroxide as a leaving group. But for those of you that haven't been through that section yet, you may remember from prior chapters that OH is a bad leaving group. And it is, except when you're in strongly basic media like sodium hydroxide. Under those conditions, because you're going to form water, eventually you can actually have OH minus be the leaving group temporarily. And then we can use that hydroxide to deprotonate the phenol, and then that would get us to the product. All right, and so like I said, there's two conceivable mechanisms here. The first one here starts with deprotonation, and it's a nice short one where we deprotonate the OH, and then we use those electrons to push all the way through to just kick off this carboxylate as the leaving group. And the carboxylate is a better leaving group than hydroxide, and based on pKa, this totally makes sense to me because it's downhill for hydroxide to deprotonate the phenol. And so if I had to pick the right mechanism, I would choose the one up above here that starts from deprotonating the phenol and then kicks off the carboxylate. Some of you might have thought about this ester attack, where we actually have hydroxide initiate at a different site on the molecule. I would say that there's nothing wrong in terms of an arrow pushing perspective from that. You can certainly go through and get to the product from that way, but you can see it's a much more complicated mechanism that involves a lot more steps. And ultimately, it's probably less favorable to kick off hydroxide than it is the carboxylate. So if I had to have a preference for one of these, I would prefer the mechanism up top here, again, that starts with the phenol deprotonation and just pushes off the ester using that group. All right, so that's part one of this question. The second half of the question that I asked my students is on this product here, how many sets of NMR resonances would you expect in the proton or hydrogen NMR, the 1H NMR? And so to do that, we have to recognize that, remember, resonance structures are not separate molecules. They're actually the same structure. And so if I redraw this species, it looks a lot like there should be, and I'm going to count these here in red, 1, 2, 3, 4, and then 5, 6, 7, 8, and those are the same. So really only 6 separate ones, 4 on the first ring, and then there's 2 on this ring because they're symmetric. These are both ortho. These are both meta to the O minus. And then the same would be true over here. So those 2 are going to be the same, and then these 2 are going to be the same. And so there should be 2 unique ones from here. And so one common answer here would be 8. The downside is that answer is actually going to be incorrect. And the reason it's going to be incorrect is because of resonance. So we can take these electrons, swing them down, push these out, move these up, move these over, and we can generate a resonance structure that now has the 2 rings swapped. And so in the resonance hybrid then, we're going to have partial double bond character across all of this. And those 2 rings from the NMR's perspective are going to be equivalent. And so what that means then is the right answer is going to be 1, 2, 3, 4. And then we're going to have all of these are going to be 5. And then all of these are going to be 6. So there should only be 6 answers, or sorry, 6 resonances in the 1H NMR for the fully deprotonated version of this molecule. And just for fun, let's go through and label all of these places where that partial negative charge could sit. So we're going to have partial negative there, partial negative there, partial negative there, and then we'll have partial negative here and partial negative there. And so if you're uncertain of that, or if you're uncomfortable with that, what I would encourage you to do is go through and work at all of the possible resonance structures, because you should be able to come up with one for each of the places where I've labeled a partial minus on this molecule. And that means that you should be able to come up with a total of 8 possible resonance structures. And so that would be a good exercise. All right, so that concludes this problem. 2 separate mechanisms for the phenolphthalein deprotonation, as well as a little bit of a discussion there from the NMR. Again, if you're enjoying these videos or if you're finding them helpful, what I would encourage you to do is please subscribe to us on YouTube. Also, please become a patron on the Patreon page if you would like copies of the PDFs of these questions, both in the unfilled out and filled out format. And so you can see them both before and after the video. Thank you again for listening. Please tell your friends about us, and please go ahead and watch the next video.